We now move to the final major section of this week, the role of petroleum geology in CCS, or carbon capture and storage. This section is very important because it shows how traditional petroleum geology knowledge can be directly applied to future low-carbon energy systems. This slide explains why phase diagrams are also important in CCS. Carbon dioxide changes phase depending on temperature and pressure. At ambient conditions, it is a gas. In pipelines, it is often transported as a supercritical fluid, and in ships it is often transported as a liquid. So just as phase behavior matters in oil and gas production, it also matters in CO2 transport and storage design. This is an excellent idea for you. We are asked, which geological trap is the best candidate for CO2 storage, and why? In general, anticline traps and dome traps are often strong candidates because they naturally provide containment under impermeable caprock or salt layers. Fault traps can also work, but they require careful evaluation because faults may either seal the CO2 or allow leakage. This slide beautifully shows how petroleum geology concepts can be transferred directly to CCS. This slide reminds us that not only structural traps but also stratigraphic concepts can be transferred from petroleum geology to CCS. Rock layer geometry, pinchouts, facies changes, and depositional architecture all influence how injected CO2 moves and where it may be stored. So petroleum geology remains highly relevant even in the context of decarbonization. This slide asks a very practical question for you: where will we store CO2 in giant subsurface sites? Petroleum geologists are experts in identifying geological formations that can securely and permanently store CO2. They evaluate rock properties, structural configuration, caprock integrity, and fluid flow behavior. In other words, petroleum geology provides the screening framework for selecting suitable carbon storage sites. After site screening comes site characterization. The same skills used in oil and gas exploration are directly applicable here: seismic imaging, drilling, core sampling, and logging techniques. These methods help us assess storage capacity, integrity, injectivity, and long-term safety. This is one reason why petroleum engineers and petroleum geologists are so important in CCS projects. This slide emphasizes that storage site characterization depends on subsurface data. In practice, such data may include seismic sections, well logs, core measurements, structural maps, and pressure information. The important point for students is that subsurface engineering is always data-driven. Good decisions about CCS require an integrated geological model built from many kinds of evidence. This slide highlights uncertainty and risk mitigation. No subsurface model is perfect, so every storage site assessment must consider uncertainty in parameters such as structure, fault behavior, caprock quality, heterogeneity, and pressure evolution. A strong petroleum geology workflow does not simply describe the subsurface, it also helps quantify uncertainty and reduce risk.